Hello, everybody. My name's Harry Nahadas. I'm the president of the East New England chapter of the Vertical Flight Society, and I'm excited to present to you today our December edition of our monthly meeting. And we've got just a terrific guest speaker who I will introduce very briefly. First, I'd just like to talk a little bit about the Vertical Flight Society, and those of you in the East New England area in particular, I encourage you to join. We participate in a number of interesting events. We host these webinars periodically, try to do it every month or so. We probably average every other month, but we shoot for an interesting topic every month. As part of Vertical Flight Society, you also get the premier industry magazine, Vertiflight, which basically all you need to do is read Vertiflight, as well as getting the weekly updates in the email, and you stay up on all the latest happenings in the vertical flight space. You also get to network with like-minded professionals. You get to attend the annual forum, which the Vertical Flight Society holds in various areas, and primarily it's a technical society. Recently, over the last 2 years, the membership has been skyrocketing, and it's skyrocketing primarily for two reasons. One is the U.S. Army's program, called Future Vertical Lift, where they're looking to essentially replace many of their enduring fleet with new aircraft. And so there's a lot of activity going on with the U.S. Army on designing and running helicopter competitions for that program. And then secondly, you probably have heard a lot about the urban air mobility space, and there's just a phenomenal amount of activity going on in that space. There are, I can't remember what the last count is, but I know Mike Hirschberg, who's the executive director of Vertical Flight Society headquarters, and I think he keeps track, and there's close to 500 companies looking at producing an electric urban air mobility vehicle, which is just very exciting, and that has also driven a lot of the growth in the Vertical Flight Society. So between those two elements, the membership is just booming, and it's quite interesting. I mean, it's fascinating what's going on, and so our speaker today is right in line with that, with a whole different dimension to vertical flight. And so we're very excited to have Professor Kevin Chen with us today. He's currently an assistant professor of electrical engineering and computer science at MIT. He received his PhD in engineering sciences from Harvard, his bachelor's degree in applied engineering and physics from Cornell, and his research interests include developing high bandwidth and robust soft actuators for microrobot manipulation and locomotion. He's published in top journals including Nature, Science, Robotics, PNAS, Nature Communications, IEEE, and so forth. He's a recipient of the RAL 2020 Best Paper Award and the IROS 2015 Best Student Paper Award and Harvard Teaching Excellence Award. His title of his presentation today is Insect Scale Flapping Wing Aerial Robots Powered by Soft Artificial Muscles. And so we can't wait to hear and see these little vehicles in action. And so if you have any questions during Professor Chen's presentation, please use the question function on the menu bar in this GoToMeeting tool. And so if you show the menu, you can see questions, and then you can type in your question. And so we're lucky enough to have with us today Chris Thompson from the headquarters Vertical Flight Society, and he's helping us sort of behind the scenes running the webinar, and then Vertical Flight Society board member Scott Hanula, who will read the questions to Professor Chen so that he doesn't have to try to read questions and answer them at the same time after his presentation. So with that, I'm going to ask Professor Chen take the floor and enlighten us about insect-sized robots.
Okay, thank you. Thank you, Henry. All right, so let's get started. So I want to talk about super tiny robots today. And I want to first address several questions together. The first question is, when we talk about tiny robot, what are micro-robots? When people think about robots, they usually think about large-scale robots, such as trains or airplanes. They span the scale of meters to the scale of hundreds of meters. On the other end of the spectrum, we can think about very tiny robot made of the MEMS technology, and they usually range from microns to tens of microns. What I want to focus on today is talking about insect scale robot, and specifically they range from 1 to 5 centimeter, and their weight range from 10 milligram to 10 grams. As a quick example, when I was a student at Harvard, I worked on a project called the RoboBee. So this project really takes inspiration from nature. Bee weighs about 120 milligram, and they flap their wings from 180 hertz to 250 hertz. We have created some robot that basically weighs in a similar range and also flap their wings in a similar range. If you look at the history of this project, you can see a fairly interesting trend. Starting from 2008, we start to demonstrate the robot at very tiny scale has enough lift capability to lift off from ground. And then we start to realizing interesting functions, such as teaching the robot to hover, teaching the robot to swim, teaching the robot to perch on compliant leaf, or more impressively, impulsively transition from water to air through a combustion. The interesting trend in our research is that we first implement functions that large traditional robot can do in tiny scale robot, and then think about interesting functions that are challenging, if not impossible, in larger scale robot. So now let's tackle several important questions together. The first question is, why do we study microrobotics? And to me, there are two reasons. The first reason is that we can implement new functions in micro scale robot by leveraging interesting physics at this scale. For example, using the same set of actuator and wings, we show the same robot can both fly in air and swim in water. And more than that, we can also use micro scale robot as a platform to investigate interesting physics at the centimeter scale. By looking at the flow field generated by a flapping wing robot, we can infer about the lift and drag generation mechanism of a small insect. And the second question I want to address is, what makes micro-robot unique? And the short answer is small is different. So for example, you can drop a micro-robot from a meter above, and because the inertial effect is very small, the robot sees very little change to its performance. And in addition, because it is small in this case, this robot can leverage surface effect and can jump off the surface of water. Again, something very challenging, if not impossible, for larger scale robots. And the third question I want to address is, what are the potential applications of micro scale robots? In the short term, I would argue there are already very interesting things we can do. So in this video, we put a micro scale robot inside of a turbine engine. And the idea is that we want to carry very tiny cameras on top of the micro scale robot, and the robot will just climb inside of a turbine engine, take videos and pictures, and look for cracks on the inside the engine. Okay. In the longer term, what we are hoping to achieve is to use a swarm of micro scale robots and deploy them in a very complex environment to do search and rescue missions. I would say that we are still very far away from this long-term vision, but toward the end of this talk, I'll come back and sort of identify the major challenges and how far we are from achieving those goals. So what I want to focus on today is sort of introducing 4 projects. I want to tell you about how those micro-scale robots are made, what kind of physical study we conduct on them to understand how flapping wing robot can generate lift and drag forces. I want to then transition to talk about new functionality, such as teaching the very tiny robot to be able to both fly and swim, and also thinking about a new class of micro-scale robot, ones that we can use to emulate the functions of small insects. So let me start by explaining to you how micro-scale robots are made. So there are several types of micro-robot that we made at Harvard. There are the basic ones that we use to fly. There are variants that we use, for example, to demonstrate improved functionality in terms of control, in terms of hybrid locomotion in air and water, in terms of carrying more payload. So the idea is to carry not only the payload, but also the batteries and the power electronics. But also there's the idea of replacing the rigid actuators with muscle-like soft actuators. So not only can those robots be able to fly, they can also robustly interact with the environment. So the goal we are trying to achieve is, for example, pollination. First, let me try to focus on the fundamental model and explain to you how this simple model is made and what are the basic components. So the simple robot consists of several components. It has carbon fiber airframes, wings made of carbon fiber and polyimide, transmissions made of polyimide and carbon fiber, and it has actuators made of piezoelectric ceramics. And because this robot is so light, about 4 or 5 years ago, we still have to rely on a offboard tether for supplying power and control. Okay, so if you look at this robot assembly, we assemble the actuator into an airframe, and then you assemble the transmission into the actuator, slot the wing hinge into the transmission, and finally attach the wing onto the robot. A unique thing about our robot is that instead of using traditional components such as motors and bearings, we use new actuators such as piezoelectric actuators and new flexures and transmissions. So those flexures are made of carbon fiber and polyimide. We laminate multiple layers of composite material together and use the compliantness of the polyimide material as a flexure. So in the next video, we are showing you how this composite structure-based actuator is working. So here you're seeing an array of piezoelectric actuator that we are trying to command at a very high frequency. And about a couple of years ago, the manual assembly process is fairly tedious. It probably takes us a couple of weeks to train a graduate student to make a micro-scale robot. And in this video, we are trying to film the student trying to sort of make the entire robot. If we have time toward the end of this talk, I'm happy to come back to this video, and that sort of shows you all the manual process for assembling the robot. Now, this is a great method for prototyping the robot. Once we have a good design, what we really want to do is to be able to make a lot of them very effectively. So instead, we came up with a new technique, which is called pop-up. So in this new fabrication scheme, what we do is we use the elastic property of the laminate, and the idea is that we would use the elastic property to assemble the robot without requiring a student. So in this case, we would make several cuts under a laser, and then the elastic material pops the robot into place. Okay, so this is how we assemble the robot. Now let's talk about how we characterize the robot and how we understand lift and drag forces that a flapping robot can do. Okay, so we have been able to create those robots about 10 years ago. The next thing we want to do is to improve the robot design so that we can carry more payload. Carrying more payload means the robot has more lift, so it has more capability in flight. But more generally, we also want to understand the underlying physics so that we can generalize what we have learned to other flapping wing systems. So let's identify the challenges first. To me, there are two major challenges for understanding insect flight. The first challenge is we want to resolve the flapping wing kinematics that often happens at a very high frequency. Those wings usually flaps on the order of 200 Hertz to 500 Hertz. How do we develop a system that allows us to make observations? And more than that, we also want to observe or measure the force that's been generated by the flapping wing motion. And on top of that, we also want to measure the flow that's being induced by the flapping wing motion. So we came up with a experimental apparatus. In this picture, we show that we place a wing driver inside of a fully enclosed chamber. We shine a plain laser onto the wing driver, and we use a high-speed camera to capture the motion of the flapping wing, but also the motion of the fluid particles around the wing, so that we can not only measure the flapping wing kinematics, but we can also measure the forces and the fluid flow. If you zoom into the platform, you're going to see a robot being mounted on a 2-axis force sensor. So in real time, we can also measure the lift and drag forces. So now let me show you how the robot operates. So in the simplest model, the robot has 2 degrees of freedom. Our piezoelectric actuator drives the wing stroke motion, whereas the wing pitch rotation is passively mediated by the compliant flexure and the interaction between the wing inertia and air. We have the capabilities of capturing thousands of flapping wing videos, so we can optimize wing design or the flapping wing kinematics. So this is one simple example that's been slowed down significantly. We have the capabilities of capturing thousands of those videos, and we developed our own motion tracking algorithm, so we can analyze the flapping wing kinematics. By tracking the key features automatically, we can extract both the wing stroke and the wing pitch motion. To a first order, we can approximate the wing stroke motion and the wing pitch motion as pure sinusoidal functions. So instead of using 2 arbitrary functions to prescribe the wing stroke kinematics, we can prescribe them using 4 kinematic parameters. So in this case, I want to emphasize that the wing stroke motion and the flapping frequency is something we have direct control of, whereas the wing pitch rotation and the relative phase shift between the pitch and stroke motion are something that we have to rely on the fluid structure interaction. So there's really a lot of fluid structure interaction we have to study and to optimize for. Now, to understand the kinematics, we have to write out models for it. The simplest model you can write out is a quasi-steady force model that allows us to predict the time average forces we are going to be generating from the flapping wing motion. Using our experimental setup, we have been able to examine a lot of interesting parameters, such as the influence of wing areas, changing wing inertia, changing wing shape, such as the aspect ratio, changing the area moment, that is shifting the center of area outward to the wingtip, or changing the leading edge profile, which will induce a large pitch-wise torque change. For the interest of time, I'm not going to focus on those studies today. I just want to present to you a quick case study of wing hinge stiffness. The idea we are trying to study here is how would a change of wing hinge stiffness impact the efficiency of flapping wing flight. So again, zooming into the wing hinge can be approximated as a compliant flexure. The stiffness of this flexure is proportional to the geometry of this flexure. And through experiments, we realized that just by changing the wing hinge geometry, we can induce a large change on the flapping wing kinematics. You can probably see those 2 videos are quite different. And those are induced just by changing the wing hinge. Okay, and specifically by just increasing the wing hinge stiffness, we can induce a negative phase shift. And by reducing the wing hinge stiffness, we can induce a positive phase shift. Why is this important? Well, if you normalize the lift coefficient and plot it as a function of the relative phase shift, you can see a strong negative correlation. So the very simple takeaway is that the experiments tell us if we just to some extent increase the wing hinge stiffness and induce a negative phase shift, we can observe a large increase of net lift. So that is a very practical takeaway. But as physicists, we are really interested in why is that the case, right? So we set out to understand the underlying fluid dynamics. So as a consequence, we implemented a numerical solver to solve an incompressible Navier-Stokes equation, and then we integrate over the shear stress tensor to obtain the lift and drag forces. On top of that, we also want to solve for the fluid structure interaction. So we have formulated a coupled ODE and PDE solver. So in one of the particular time step, not only are we solving for the instantaneous flow field, we are also using the torque generated by the flow field to solve for the wing pitch motion. So first, let me show you a sample 2D simulation. In the 2D simulation, instead of concerning the motion of the entire wing, we just focus on one particular wing chord. In this case, we project the motion of this one particular wing chord on 2D plane and approximate the rotational flapping motion of the wing as a 2D planar translation. So in the next video, I'm showing you the X and Y components of the flow field, the pressure field, and the verticity field. Okay, so it's very intuitive to look at the verticity field because that tells you how is the leading edge and trailing edge vortices being generated, and we can infer about the leading edge circulation and then use that idea to estimate the lift and drag forces. Now, this looks like a very interesting simulation, but we also want to validate the simulation. So we conducted at scale PIV experiments. And the idea is, again, putting in oil particles in the chamber, use a plain laser to illuminate the flapping wing motion, and try to observe the flapping wing kinematics. So the next video shows a sample PIV experiment, again, slowed down quite dramatically so you can see the motion of those particles. If we compute the cross correlation of this high-speed video, we can obtain the instantaneous flow field. And if you compute the curl of this flow field, you can obtain the isoverticity field. Okay, so the next idea we want to do is to compare the isoverticity field we have been able to generate with the simulation. Qualitatively, I would argue those look quite similar, but quantitatively, a key difference between simulation and experiment is that in the experiment, the previously shed vortex tend to decay much more quickly than what we see in the simulation. Okay, and it is not surprising in some sense because the experiment is in 3D and the simulation is in 2D. And in fact, this sort of a key difference would lead to a difference in the prediction of lift and drag forces. So as a consequence, we realize that the prediction of our 2D simulation usually leads to about a 30% error compared to experimental measurement. And that really is contributed by the fact that we are ignoring the rotational motion from the wing. To correct for that, we implemented a full 3D CFD model. In this case, the simulation is much more involved. And based on the 3D CFD model, we have been able to sort of consider the influence of the wing shape and also see a fluid mechanical phenomenon, which is called spanwise flow, right? Because now the motion is rotational, you can generate a pressure gradient from the wing root to the wing tip, and this spanwise flow contributes significantly to stabilize the leading edge vortex. But again, a simple takeaway is that by implementing 3D CFD model, we can dramatically reduce the modeling error. And more than that, if we come back to the previous experimental observation and try to justify that using all of the suite of computational and experimental tools, we realize both in experiment and in simulation, we observe that the relative phase shift is strongly negatively correlated with the mean lift coefficient. And in addition to make the observation that negative phase shift leads to larger lift, we actually can explain the underlying phenomena by observing that also corresponds to a larger leading edge vortex. And from the aerodynamics, if you have a stronger leading edge vortex, that usually leads to stronger leading edge circulation, which translates to higher amount of forces. Okay, so the main contribution of the first project is really using a suite of computational experimental tools. We have proposed a new wing design, which significantly improved the vehicle payload. And this new wing has been incorporated into our new robot to demonstrate new functions, such as carrying a electro adhesion pad to perch on leaf, or even carrying a tiny camera. We can also incorporate our new wing design into larger platforms so the robot can carry more payload. And in addition, we are excited to see that groups elsewhere are also start to adopt our wing design. So the first part of our talk really built the foundation for what I want to demonstrate, right? This is a lot of physics and CFD analysis. Now let's try to use those conclusions to implement some interesting functions in the small-scale robot. In the next project, I want to transition and change here to talk about robot functionality. Specifically, I want to talk about hybrid aero-aquatic locomotion. And I want to start by a quick motivation. The physics question we want to ask ourselves is that is there any similarities between flapping in air versus flapping in water? And if there is similarity, can we teach a micro-robot to do interesting things? So we came up with a new project proposal in the sense that we want the same robot to be able to fly in air, swim in water, and transition from air to water, and transition also from water back into air. And again, let's identify the major challenges. To me, there are two. The first challenge is using the same set of actuators and wings to both fly and swim. And the second challenge is to be able to overcome surface tension effect so that a tiny robot can transition from air into water and from water back into air. So let's first address the challenge of multimodal locomotion. We first turn to nature for inspiration. Puffins are very amazing animals. They can fly in the sky. They can take a dive into water. Once they're under the water, right, puffins change their flapping frequency so they can swim around and chase for prey. Using this very similar idea, we proposed a very simple quasi-steady analysis that predicts the flapping frequency in water based on the flying frequency in air. And then we look at the change in the Reynolds number, and we realize that to our surprise, the Reynolds number actually remains quite similar. So using our computational tools, we predict that the lift and drag forces of those systems to be quite similar in both water and air. And then we conducted flapping experiments. So the next video really builds the foundation for everything that follows. As you can see, by just slowing down the flapping frequency in water, we can generate similar flapping kinematics. This is again significant because let me remind you that the wing pitch dynamics is passive. So the fact that we are able to generate similar kinematics really implies the robot can generate similar forces in air and in water. So motivated by that experiment, we insulated a robot and we tried to swim this robot in water and observe what would happen. You know, not too surprisingly, the robot can flap around, it can jump around, but it's not really doing a lot of things underwater, and it quickly falls over because without control, this robot is intrinsically unstable. What was surprising to us is if you turn up the flapping frequency to about 10 Hertz, all of a sudden you achieve a passive upright stability, and you see the robot can passively swim to the air-water interface without any feedback control. And that is something that's both surprising, but also very interesting to study. So we look at high-speed videos of the robot swimming and realize that as you increase the flapping frequency, the robot pitch dynamics become smaller, and all of a sudden it has this property of passive upright stability. And we write a 10 degrees of freedom model to study the stability property of the robot. For the interest of time, let me not go into the details of the model, but just tell you the key conclusions. The key conclusion is that unlike flying in air, the drag force on the robot body helps to stabilize the robot in water. And this drag force on the robot body allows the robot to stabilize without even feedback control. Okay, so in both experiments and in simulation, we've been able to show that indeed the robot can swim up to the air-water interface without using any sort of feedback control. And that is very significant because feedback control is very hard underwater, whereas it is much easier to be done in air. So the next question that we ask is, well, can we passively stabilize the robot in air as well? And we can. but the cost we have to pay is to put on huge sails on the robot. So one of my colleague, Professor Sawyer Fuller now in UW, he has put on huge sails on the robot, and he showed that without feedback control, the robot can passively stabilize in air. But again, this is something that we have been able to do for free in water. So about 5 or 6 years ago, we demonstrated that for the first time, a 70 milligram robot was able to take off. And at that time, it has to plunge into water because transitioning from water into air was very challenging at that time. And once the robot is under the water, we turn on the robot at a much lower frequency. The flapping frequency reduces from 100 hertz to about 10 hertz. And as you can see, the robot can passively swim to the air-water interface again. So that was an exciting demonstration for us. But in some sense, the robot is still limited. You can see the robot cannot transition from water back into air again. So now let's address the second part of the challenge, which is trying to teach the robot to transition impulsively from water back into air. Okay, so now let's think about what kind of challenge would surface tension impact on a tiny scale robot. To me, there are two major challenges from surface tension. The first problem is that the surface tension pushes down the robot and causes the robot to be unstable, right? So in this case, the robot flips over. The second challenge is that the surface tension at this scale is much, much larger than the weight of the robot. As humans, we barely feel surface tension. Surface tension is less than 0.1% of our weight. But for a tiny robot like this, surface tension can be 10 times larger than the weight of the robot. And it's also 3 times larger than the maximum robot lift. So a simple takeaway is that direct water-to-air transitions through just flapping the robot wings is impossible. So how do we solve those key challenges? Well, if we want to solve those two problems, let's think very carefully about surface tension. If surface tension is very strong, why don't we use the second problem to solve the first problem? Namely, let's utilize the surface tension to stabilize the robot on the water surface. And to solve the second problem, we realize that although surface tension is very strong, it's singular, meaning that it only exists at the water surface. So in this case, we developed an impulsive mechanism that can generate a very large force just at the water surface, and we can use that large impulsive force to push the robot out of the water surface. So that brings me to a two-step transition process. In the first step, we are going to use electrolysis to split water into a combination of oxygen and hydrogen. And in the second process, we are going to use a combustion process to impulsively ignite oxygen and hydrogen so that we can push the robot out of the water surface. Now that brings me to the new robot design. In this new robot design, we have new wings to generate more forces. We have compliant triggers to maintain the stability on the water surface. And I think more interestingly, we have a combustion chamber in which we use to split water into gases, but also to use it as a combustion chamber to generate large impulsive forces. So first, let me show you how the robot works. With the buoyant out triggers, we are able to leverage water surface tension effects to stabilize the robot on the water surface. And what I want to spend more time on is sort of show you the gas collection chamber. Okay, the gas collection chamber is responsible for the impulsive takeoff from water surface to air. If you zoom into the gas collection chamber, it's consisted of a titanium and polyamide top pieces and 4 carbon fiber side pieces. And if you zoom into the center, we have a multifunctional component in the center, consists of a sparker plate and a parallel plate. How does this multifunctional component works? Well, if we turn this component on at a low voltage, then this parallel plate will start to split water into gases, namely hydrogen and oxygen. And those gases will be captured by the gas collection chamber. And afterwards, we're going to send in a high voltage to the sparker plate, and we're going to use that to ignite the mixture of hydrogen and oxygen. Okay, so let me show you how this works. First, we turn on a low voltage, and you can see that the small bubbles in water starts to signify that the water is being converted into a combination of oxygen and hydrogen, and those are captured in a gas collection chamber. Once the chamber is full of gases, we are going to ignite the gases using the sparker plate. As you can see here, by sending in 200 volts, we can generate a tiny spark which will ignite the mixture of hydrogen and oxygen. Now let me put everything together and show you how the robot works. We start at the bottom of the tank, and the robot will flap its wings to swim to the air-water interface. Once the robot reaches the air-water interface, we are going to split water into gases, and you will see that this chamber starts to collect hydrogen and oxygen, and the buoyancy force slowly pushes the robot wings and transmissions and actuators out of the water surface. Once the wings are out of the water surface, we flap the robot for a little bit to dry the robot, and the robot prepares for impulsive transition. Now I recommend you to focus on the next part of the video because it's going to be quite quick. We now ignite the mixture of hydrogen and oxygen, and as you can see, this quick combustion breaks the water surface and pushes the robot out of the water surface. This combustion completes within 1/1000th of a second and impulsively drives the robot out of the water surface. Okay, so we spend a lot of time trying to make sure the robot won't break. And also, unfortunately, the robot cannot immediately fly after this combustion. It has to land on ground, take about 5 minutes to dry itself, and then it can fly again. So again, I recommend you to pay close attention to the next video because it's going to be played in real time and it's going to be very quick. So, we put the robot in a small beaker and we ignite, and as you can see, this combustion happens within 0.5 seconds. The robot takes off and passively lands on ground. Right? Now we are playing the same video at 200 times slower, and you can see the robot sort of takes off and it passively lands on ground. Okay, so to summarize, we have created a 0.1 gram robot that can do multiple things in fairly complicated environment. Specifically, the same robot is being able to fly in air, is able to swim in water, is able to impulsively transition from air to water and from water to air, and also it can passively land on ground. Once the robot is dry, we can take the robot to air again. So the theme of our research is really very tiny robot can do multiple things in very complex environment. So now let me transition to introduce a new project. In this new project, instead of focusing on multimodal locomotion, we now think about a new form of actuation for those tiny robots. Just zooming out a little bit, let me say that our longer-term vision is to create a swarm of ubiquitous and multifunctional microscale robots that can perform realistic tasks in complex environments. Whatever robot that I've shown you today has been able to demonstrate precise locomotion, and they operate at a really high frequency, but they're still limited in some senses. At Harvard, my colleague and my previous faculty members are sort of solving key problems in microrobotics. They are putting in lightweight actuators. They're trying to develop new controllers. They're also trying to put in power electronics for those microscale actuators. But what I want to focus on today is addressing the fabrication scalability of the robot, and also addressing the fact that microrobots are very difficult to make, and therefore everything that I've shown you today involves a single robot performing in complex environment. How do we scale up the number of robots, and how do we make a lot of robots more efficiently? I propose that we look into a new direction, a new field called soft robotics. For a very long time, people know how to make a lot of soft robots very, very, very efficiently. And soft robots have their own control method. In the past 5 years, most of them are controlled open loop, and more recently, people started to use closed loop control for those soft robots. And in addition to use batteries and they now start to use pneumatic sources and also chemical sources. But soft robots also have limitations. Most soft robots' functionalities are inferior compared to micro-robot, mainly because they are unable to operate at a very high frequency. And if you cannot operate at a high frequency at a small scale, you probably will not be able to generate large forces, and therefore the robot wouldn't be able to fly. So our recent research thrust is to create a new class of micro-scale robot, and namely, we want to combine soft and rigid components to make micro-scale robots that are both agile and efficient, but also very robust and capable. So what I want to talk to you about today is focusing on a new type of robot that we have created that consists of both very precise micro-scale rigid component for effective interaction with the environment, but also soft actuators that look like human muscles that can operate at high frequency and that they are robust to collisions. Okay, so what I want to convince you today is that this class of micro-scale soft robot can not only fly, but also demonstrate new functionalities, such as sensing collisions, surviving collisions, or even aggressive maneuvers, such as performing a somersault in air. So first, let me introduce to you about those soft actuators. You know, for a quite long time, we have played with rigid actuators. Those actuators are great. They have high bandwidth and excellent controllability. One of the limitations they have is they have very small motion. As a consequence, we really need to train our graduate students to be very careful in making tiny scale robots. On the other hand, we can make robust dielectric elastomer actuators that functions like human muscles. They can operate at relatively high frequencies, in this case on the order of 500 Hertz, but more surprisingly, they have large strain, which means that they are robust to assembly error and they can tolerate large assembly error, which means that soft robots made of those type of soft actuators can be made very, very easily. We have incorporated the soft actuator into our flapping wing robot, and in this video, you can see that this robot flaps at 300 Hertz. So this is a quite impressive result in the field of soft robotics. Quite counterintuitive to see how soft actuators can operate at such a high frequency. We have achieved this result about 2 years ago, and motivated by this, we started to demonstrate takeoff flight. And as you can see in the next videos, right, the robot actuator really behaves like muscles. They contract and they elongate and they push the wings to flap and back and forth. So this is a very exciting video for us. For the first time, we show that soft actuators have enough power density to enable takeoff flight. But from a robotics perspective, you can also see that this is probably still limited. The robot falls over within about 0.1 seconds and is intrinsically unstable. So from a functionality perspective, this is really not very useful yet. So the next goal we have is to stabilize this robot. So we put two units together and we used a phenomenon called precession to stabilize the robot. That is, if we think about our robot as a spinning top, and if we can trigger a very fast spinning motion, we can use that precessional motion to stabilize the robot. Okay, again, to argue about stability rigorously, we have to write out the equation of motion. We have to look at the relative contribution from the yaw torque and the angular speed of the robot. For interest of time, I'm not going to go into the proofs, but let me just show you a sample simulation and experiment. In both experiments and simulation, we again show that this idea of passive upright stability is extremely important for tiny scale robot. In this case, without any sensing or feedback control, the robot was able to achieve passively upright ascending flight. And that is something that was quite exciting to us. This robot in this demo was able to fly at a speed of 30 centimeters per second. So that was one step forward towards creating flyable soft robot. But the big question that we want to ask is, are soft robot controllable? Right? I've shown you with one unit of our robot, the robot can take off. With 2 units, we can achieve passively stable ascending flight. The key question is, can we achieve controlled hovering flight using this 4-unit robot? So again, let me skip the controller design, and let me just show you a quick video that shows indeed we've been able to demonstrate that soft aero robot was able to achieve controlled hovering flight. So again, this is about 2 years ago, we demonstrated the soft robot was able to hover around the set point. And as you can see, the robot is still not quite stable, right? It can hover around the set point, but it drifts a little bit. Toward the end, I'll show you a better hovering video. So in this particular demo, we show the robot was able to fly for about 15 seconds, and it hovers around the set point, and the air around the hovering set point was on the order of 3 to 4 centimeter on the X and Y axis, and it was about 1 centimeter on the Z axis. Okay, so we've demonstrated that soft robot can do a lot of the functions that rigid robot can do. Let's now think about new functionalities. A quick thing that I can think about is robustness, right? Like insect, we repeatedly run the robot wing into an obstacle, and the actuator sees no damage. In fact, not only does the actuator sees no damage, we can detect collisions by measuring the instantaneous current changes in the actuator. So if you're trying to fly the robot, as soon as the robot collides with an obstacle, we can detect that collision and send in control signals to stabilize the robot. Okay, so with that, we have a more robust platform. So we've been able to demonstrate we can fly 2 robots at the same time. And in this case, we show that we intentionally run both robots into a wall just to demonstrate they're very robust. Unlike previous robots, you have to be very careful. In this case, you can run them into obstacles and they see no damage. And in addition, you can try to collide 2 robots into each other. In this case, you can see the robot try to push down each other, and the robot still survives those collisions. Okay, and taking this one step further, we want to implement more functionalities in those robots. So we take inspiration from the very famous robot at MIT. MIT has small cheetah, and we can see that people can kick on the small cheetah and it will recover stability. And the small cheetah is very powerful, so you can also try to do a somersault in air. Okay, so the next thing we want to do is to emulate similar functions in our robot. So what's going to happen, when the robot is flying and you're trying to hit the robot, right? So one thing we are trying to demonstrate is when the robot is trying to fly, we try to hit the robot, and the robot can recover to the hovering set point. In this case, we introduce a fairly gentle collision. In the second experiment, we try to hit the robot slightly harder. Specifically, we try to push on the robot actuator. Okay, and as you can see, the actuator survives the collision. And then you also try to push on the robot wings, and the robot can also survive that collision. This is, it won't be so easy if you sort of try to crash into a quad rotor, for example. And this final demo, we try to hit the robot quite hard, the robot bounces on the floor, and then it returns to the hovering set point. So really, we are trying to demonstrate insect-like robustness in those robots. The second thing we want to demonstrate is that we want to show the robot can demonstrate aggressive maneuvers. In simulations, we try to show the robot can take off, and it will ascend upward trying to do a somersault, and then it will try to recover to the set point. Okay, so trying to do a somersault in simulation isn't too hard. Let me show you how the robot is trying to do it in real time. So again, it's going to be a little fast because a small robot usually fly in a very short time scale. In real time, you will see the robot will take off, hover around the set point, and then it will try to go up, flip, and then recover to the set point. Now let me show you the same demo, just played slow. Okay, so the robot will take off and hover around the set point, and then it will ascend upward. Once it reaches a target, it will try to do a somersault. Okay, once it completes the somersault, it will try to recover altitude. We didn't have enough clearance in our flight arena, so it bounced on the floor, but then it eventually recovers to the hovering set point. So this demo again consists of several steps. The robot first tries to take off and hover, and then it tries to ascend, and then afterwards it tries to perform a somersault, and then it tries to recover altitude, and finally it will remain at the hovering position. So in this 5-second hovering demo, right, we demonstrate the robot has the capability of take off, hover, ascend upward, trying to do a very quick flip, and then eventually recover to the hovering set point. In fact, we can repeat this demo for 5 times to demonstrate the robot can survive collisions, and it's very robust. So in summary, we have created a soft robot that is both robust and agile. By robust, we mean the robot can survive in-flight collisions, and by agile, we mean that the robot can do very aggressive maneuvers, such as a somersault in 0.15 seconds, or it can also fly at a relatively fast speed up to 70 centimeters per second. Now, it may not be fast compared to large-scale airplanes, but considering this robot has a land scale of 1 centimeter, thinking about how small it is, this is really a quite fast flying speed. And just let me very briefly say that our goal, in addition to make robust and agile robot, is to demonstrate robot can be very precise, long endurance, and power autonomous. So this is a very recent video that we are able to achieve. And as you can see, the robot fly for 20 seconds, and now the flying motion is very stable. The attitude error is about 2 degrees, and the position error is about 1 centimeter. So we are really spending a lot of time to improve our small-scale robot. Finally, just a few words on power autonomy. We acknowledge that soft robots are still inferior compared to rigid robots in terms of power autonomy. If we do compare with the state-of-the-art rigid robot, we realize that soft robots' power density, lift-to-weight ratio, actuation voltage, and efficiency are way lower, which poses a significant challenge for achieving power autonomy. But we are improving quite quickly, right? Over the past 2 years, we've been able to improve the power density of soft actuator, lift-to-weight ratio of our robot. And really, very recently, we will have a work that come out, hopefully in the next month or so, that shows soft actuators' power density and lift-to-weight ratio is catching up to the state-of-the-art. And more impressively, the actuation voltage is significantly lower to about 500 volts. And that really creates a lot of opportunity for us to create power autonomous circuit for, or power electronic circuits for those tiny robots. And finally, just talk about future directions. Some of the things we are pushing for in our lab is to create a multiple wing robot. Dragonflies are something that's very fascinating. I'm always very interested in studying the aerodynamics of multiple wing interactions. We are collaborating with Professor Rob Shepard at Cornell to look at combustion powered robot. This case, this robot is powered by compressed air, and it was flapping at 165 Hertz. We are thinking about collective flight of a large number of robots. And in fact, we have a small flight arena set up in MIT just a few weeks ago. So, when you guys have time, you're definitely welcome to come to us, and we are happy to demonstrate controlled hovering flight for you. What we want to do in the long term is to be able to fly multiple of them controllably in the flight arena. And finally, we are also thinking about multimodal locomotion, that is training the robot to do multiple things in complex environments. And finally, just want to zoom out and think about this long-term challenge of deploying a large number of micro-scale robots in a very complicated environment. I would say that we are still very far from it, but also think about the promise of using a large number of micro-robots. If we have a robot that has 10 kilograms of payload, that would translate to carrying over 100,000 of micro-robots. Imagining using up to 100,000 of those micro-scale robots to collectively sense or search for survivors in this very complicated environment. I would argue that the next 10 to 20 years is going to be a very exciting time for people working on those micro-scale systems and thinking about applications of those micro-scale systems. So with that, let me end here, and I'm happy to take questions. Thank you.
Boy, wow. Thank you, Professor Chen. That was absolutely fascinating. And so now it's time for the surprise pop quiz on some of those
Yeah.
equations you were showing. Yeah. All right, just kidding. So we probably just have time for a couple of questions. And so Scott.
We have a couple here. One's pretty short, Harry, and the other one is be interesting to hear answer. But this was one of the more fascinating topics we've had on a direct usage basis. It's been cool to see the videos. So thank you, Professor Chen.
Thank you.
So somebody really enjoyed the talk, and they were wondering if the PDF of the slides would be available for share.
Sure. I think I've already shared the PDF with Chris yesterday, so definitely we can share that.
Okay, that's great. Thank you. The next one is whether or not the robot needs to be reset somehow between ignition, or is it completely reusable? And what you also showed that the second part of the question was about what happens if it doesn't land upright, but I think you answered that later on.
Right. So yes, we actually spend a lot of time to optimize the combustion process. If you're not careful, then the combustion can really explode the robot into pieces. What we did, again, I don't have the time to go into the physics of combustion and cavity and all of those, but let me do say that from the experiment perspective, the robot can survive up to 5 or 6 consecutive combustions. So the idea is that we don't need to repair or fix the robot for up to 5 or 6 combustions. After that, you do need to check the robot to see, if there's small cracks on the robot, if you need to apply extra super glue, etc. Okay.
Great. The next one is what's the limiting factor for restricting the flight? The endurance that you have for like 20 seconds. What's driving that?
Oh, I see. So right now we only fly for 20 seconds, mainly because our control, the control hardware has some limitation in the memory. So I think our control hardware can only continuously run for about 35 seconds, and it can only log so much data. The one thing I do want to say is the robot is being controlled at a super high feedback rate. The feedback frequency is 10,000 hertz, right? So the computer is really doing a lot of computation, logging a lot of data. We are trying to upgrade our system recently, and the goal, hopefully in the next year or so, is we can demonstrate, hovering flight up to the scale of a minute to 2 minutes. But what I do want to say is that if you look at how insects fly, they also don't fly for a super long time,
right?
Mainly because they cost a lot of energy. So I think our primary research focus right now is to think about how to improve the efficiency of soft actuators and incorporating power electronics on board. So that involves lowering the actuation voltage, improving the conductivity of the CNT network, but also come up with new circuit design so that we can one day put power electronics and batteries on board. So that is something I think is a grand challenge in this field.
And then one last question, just briefly. Is there a size limit to the flapping wing design? Have you found the upper threshold of that?
So I think if you compare rotary flight with flapping wing flight, I think my understanding is that rotary flight is definitely more efficient. But flapping flight, because it's operating at a much larger alpha, so angle of attack is much larger, and it's dealing with shedding of vertices, the lift per area is larger, right? So it's more advantageous to build small-scale flapping wing robots because at that scale, we definitely need more lift forces. If you want to build large-scale flapping wing robot, sure, but my intuitive feeling is that they will not be as efficient as fixed wing aircraft or helicopters. In terms of scaling, I think I've seen flapping wing robot as large as 20 grams or so. But again, when you're at 20 grams or so, you want to use motors rather than those kind of soft actuators or piezoelectric actuators. We are really operating a scheme in which the scaling of motors is not it's not great, meaning that it's very, very difficult to make very tiny EN motors that's lighter than 0.5 grams, for example. So the insect scale is still something we want to focus on. But of course, if you want to scale up, use motors, you can probably build a flapping wing robot on the order of 20 grams or heavier.
Thank you.
Okay.
Okay, wow. Well, again, Professor Chen, thank you so much. That was absolutely fascinating. Really appreciated you going into the detail and you know, showing the actual equations on how things are calculated. That's just incredible. And so thanks everybody for tuning in, and stay tuned for our next notification. Probably we're shooting for sometime the end of January to do our next webinar. So thanks again, everybody, and thank you, Professor Chen.
Yeah.
Out
Thank
here.
you.
Thank you.
Thank you, Harry. It's super fun to share our work here. See you.
Correct.